All right, so today we're going to take it a step further. We said that when you were learning how to substitute in place of those summation of 1, summation of k squared, that we were basically going to be applying that to Riemann sums. Well, today is that day. And so before I get into that substitution and what that looks like, I want to start with what we already know, okay? And so the first thing when we look at a Riemann subs, and I'm even going to use this triangle, which of course we could find the exact area. And so let's just do that before I even do the approximation. If I wanted to find the area of a triangle, that would be area equals 1/2 base times height, right? And so the base of this is 6, and the height of this is 12. And so I would do 1/2 of 6 times 12, which of course you could multiply the 6 times the 12 and then divide by 2. You could divide the 6 by the 2 first and then multiply. Regardless, you're going to get 36. And so that's the exact. That's really, I mean, now we can kind of see this is our goal. This is what it should look like. Well, let's just see what happens if we did 3 subdivisions. Again, the length of that interval is 6. We're going to divide it by 3. So that gives me a 6 divided by 3. That gives me 2. So I'm going to put 2 on the outside, and I'm going to figure out 3 different heights, correct? And so my first bar would be measured at 2. Then we would have another one at 4, and then the last one at 6. So I'm going to do a f of 2, f of 4, and f of 6. Since we have the equation there, 2x, we're going to just plug that in to get what those are. And hopefully that's relatively easy for you. So we have 24 times 2, which is 48. Now, that's a decent approximation, but you'll notice it's pretty far from what the exact value is. Let's try 6 subdivisions. 6, of course, would mean 6 divided by 6, rather 1. And so the 1 would be on the outside. Again, 6 heights that we're going to figure out. And those bars would be at 1, 2, 3, 4, 5, and 6. So we're going to do f of 1, f of 2, f of 3, f of 4, f of 5, and f of 6. And so to do that, 1 times 2, right? So 2, 4, 6, 8, 10, 12. You add these things up together, 30, 42, so I'm getting it's 42. And of course, you notice we're getting closer to that 36, aren't we, as we added those subdivisions. Well, what if we did 5 subdivisions? Of course, 5 subdivisions, that's not as pretty as the others were. We'd have 6/5, and that can't get any better, so I'm just going to leave it like that. Let's just think through this. So my first one would be at 6/5. The next one would be at 12/5. The next one would be at 18/5. The next one would be at 24/5. And of course, the last one would be at 6, right, which is 30/5. And so we'd plug those in, we multiply by 2, right? So you'd have 12/5 here. And you'll notice, even if I can simplify, I'm not going to, just simply because it keeps everything with the common denominator. And even that 6 there, you might think, oh, well, you could make that as 6, not 30/5, but it helps that everything has a common denominator. So that as I multiply this out, or rather add this together, multiplying isn't such an issue, but when you add things together, it makes it a little bit nicer. For example, these are already a common denominator, and I can combine those to get 60, correct? And I've got 48 and this 12. Those two also make 60. So that gives me 180 over 5 on the inside and 6/5 on the outside. So I have 25 on the bottom, and I would have 0, and it looks to me like I would have 1,080 over 25 as being my answer. And so we really can't tell, you know, how great that approximation is, but we can assume that since it's 5 and not 6, that it's a little worse than the 6 subdivisions that we just did, and it's about 43 something. So that's what that is. All right, well, what happens if I want to do n subdivisions? In other words, this could be any single number. Now, the cool part about this is, and I guess one of the things that if you saw this right away, it may give you a little more incentive to do it. But if I had figured this out first, right, if I figured out n subdivisions first, then what would happen is I could say, okay, this is what we use as like a generic formula almost, and then I can plug in whatever number of subdivisions they give me, 5, 6, 3, and I'll show you what I mean here in a second. So let's just say there's n subdivisions. Let's think about the process that we did. Every single time we took the length of the interval and we divided by the number of subdivisions. And so that would mean 6 divided by n. And that would mean, how many blanks would I have? You would have n of those blanks. The first bar that we had, the first spot, was 0 plus, so it was 0 plus 2, or 0 plus the 1, and that's how we got the f of 1, or the f of 2 as you saw above. Or in this case, we had 6/5 was the measure of the bar, so my first one was measured at f of 6 over 5. So this would still be, this would be measured at f of 6 over n, sorry, I almost said 9. And then the next one would be f of 2 times 6 over n. In other words, 12, right? We would do this second one, just like you did here with the 12 over 5. And then we had f of 3 times 6 over n. And how many of those did you just do with this 6/5? You did 5 of them, right? Because there were 5 subdivisions. So in this case, we would have to do n of them, and it would look like this. F of n times 6 over n. And if you thought about that mathematically, that would mean your n's would cancel out, leaving you with f of 6. So when there were, and let's just scroll up here for a moment, when there were 3 subdivisions, we went 1, 2, 3, right? We had to go all the way to 3 of those, okay? In fact, if I was to just look at what we did here, this is f of 2, right? And then this was f of 2 times 2. And then this was f of 3 times 2. And even more so, I could be even more vague and say, instead of saying 2, say 6 over 3, and use that 6 over 3 there, and you can see, oh, the 3's would cancel out, because however many subdivisions are, that's how many blanks you want to do. Similarly here, if I said, oh, this is f of 6 over 6, and then this would be f of 2 times 6 over 6, and then f of 3 times 6 over 6. And you're like, yeah, but they'll simplify. Exactly, which does make them nicer to deal with. But again, what this advantage will do with the n subdivisions is that we will see that, oh, I put the n there because as I'm talking about it, we will notice the patterns and be able to actually eliminate some work in the end. So let's just see what happens here, okay? So I hope you understand why we go up to n, and you'll notice I do that dot, 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 indicating that there are many more, but we just need enough to set up a pattern. And so what happens when I plug 6 over n into our equation? Well, that would just be 2 times 6 over n, and the next one would be 2 times that 2 times 6 over. Whatever is here, right? Whatever is here is going to go in that spot of the x, which was 2x. So this would be 2 times 3 times 6 over n, dot, 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 and 2 times n times 6 over n. And the idea is, even though you're like, why are you writing it like that, not multiplying out? Because what we want to do is we want to set up patterns. We want to get it to a way that we can work with and make a prettier equation. And for example, what do you notice that's going on in here? What does every single term inside these parentheses here, what does every single one of them have? Well, first of all, we have this 6 over n on the outside, so I'm going to leave that there. Now I want you to think through that again. So what things are inside those parentheses? There's a 2. I hope you saw that. What else is inside there that we can see in every single one of them? If you're paying attention, every single one of these has a 6 over n. Now it's tied up a little differently, but it's done through multiplication. And so we're okay. We can take a 6 over n because that's what the distributive property allows me to do. Because they're multiplying to every single term, every one of them. So we're pulling out what's in common. What's left behind in each of these, this is kind of interesting. In this first one, it doesn't look like anything, but that means we divided everything out, so that's a 1. The next term, what's left is this 2 is the only thing that's left. In this one, the only thing that's left is the 3. And guess what? Dot, dot, dot. What's the only thing left here? Now, I don't know if you're starting to see the beauty of what's going on here. What does this look like? How could we rewrite this? And to give you a hint, I want to write this using sigma. And yes, it's going to start with 1. And yes, it's going to go to n because we started at 1, we ended at n. How could I rewrite this so that it's written as a sigma? It is k. And so in front, I'm just going to now multiply this stuff out. I have 6 times 6, which is 36. I have 72 over n squared. Now just watch this. This is very cool. This is really, really neat. This is like one of my favorite things to show people. Because when you see this unfold, this is just absolutely beautiful, the mathematics here. The summation of k, if I was to scroll up for you, for those of you that haven't memorized it yet, summation of k, so we're going to just take that, we're going to use that here. So the summation k, in place of that, what I'm going to do is I'm going to put 1/2 n squared plus 1/2 n. Now just watch this. 72 divided by 2 is 36, right? This n squared would cancel with that n squared when you first distribute it. Plus, 72 divided by 2, again, is 36, because this is going to both parts. This n would cancel with only one of those, leaving an n on the bottom. Now, what I would like for you to do for class tomorrow is I would like for you to explain to me how, or rather, what is the significance of this number here? And if you can explain this, that's even better. I might even give you a bonus for that. But I want you to explain to me what this number is and how amazing this just presented itself, that we are now able to find, just go beyond just, oh, we're just going to crank out some numbers. And we'll practice these again tomorrow.